Hi, this is Christopher Boucher, and I'm going to review confidence intervals and t-distributions. Okay, we'll get started. So this section it covers the t-distribution and confidence intervals, and they are frequently put together, and that's because of a couple reasons, but we'll go over it. We'll go over it in the notes. Primarily, it's because we are to the phase in statistics where we're now starting to look at other similar distributions to the z distribution when we have, let's say, data that is not necessarily as normalized or we're a little bit unsure about, but with certain types of adjustments, we can still apply some decision making to it. And one way that we can do that is with confidence intervals. So with confidence intervals, it's one way that we can look at a range of what the mean should be, or the probability that the mean will be around a certain number, and that's what a confidence interval essentially is, and we'll talk about it more. Okay. So this says the student's t-distribution. Okay, the t-distribution takes its name from William Seeley Gossett in his 1908 paper Biometrica, pinned under the pseudonym student. So the deal was he was I believe he was here it says he worked in a brewery. Well, he did a lot of sampling in the brewery, and he figured out this t distribution, but he didn't want to get in trouble, so he wrote this paper under the name of student, and later they figured out who wrote it, but that's why it's labeled student. It was a way of being anonymous. So here's the some of the main parts of why we use the t distribution. And it says the t distribution is used when the population standard deviation is unknown, or so the population standard deviation is unknown. Okay, so right off the bat, so we're unsure about the population standard deviation, so we're going to have to make some adjustments, and we're going to probably lose some precision just based on that statement. Then the other one is the sample size is small, meaning less than 30. Okay, so it's less than 30, as we described before in one of my other ones that, let's see, with sampling distributions. We talked about normalized data and how usually around 30, the data is considered normalized at that point. Now, 30 isn't the magic number cut off 100%, but it's a number where it's around the range where people believe that the data is normalized. Like I said in the other video, if the sample size was 29, that might not be a problem either. It's just 30 is the point where most people have decided that it's probably normalized at that point. And then the third one, it is unknown if the sample comes from a normalized distribution. So one of the deals with the sampling distribution, and we talked about the theorems and some of the rules there. It was if the sample comes from a normalized distribution, then we assume that the sample is normalized, and those are probably the general rules. So in this case, the t-distribution, it is essentially what I would say all of the reasons why we would use the t-distribution and not the z-distribution. So the t-distribution is the prime of that. It's all of the other times when we don't use the z, we use the t, and that's kind of the way this is. So it says characteristics of the t-distribution. So it says it has fat tails. So if you take a look at this, it says the red curve in the image on the left is a t-distribution compared to the normal distribution in blue. So what happens is, if you think about a normal distribution, we have it's technically a perfect normal distribution would be very pointy. So the data would be very grouped towards the middle. And it makes sense because with everything with the frequency of the data, it's going to group towards the middle, and very rare events end up being on the far edges, the tails. So when we are less sure if the data is normalized, then what happens is the point of the distribution, meaning and this is the red one, the point will come down and the tails get wider. And that's because some of the probability that our actual, in this case, our actual, say, mean of the point that we're looking at that comes from, say, a population. But in this case, because we don't have as good of information, it ends up that some of that probability of where that point lies can end up in the tail, and so the tails get larger. And that's just that's, I guess, a side effect of the distribution and what it stands for. And it stands for something that's very similar to the Z distribution, but it is a little bit more distributed throughout the distribution, and it's not quite as centralized in its grouping. It's not as tight in its grouping, and that's one of the precision issues of the T distribution. It's not as precise in the way that we can do some of our measurements with it. We can still come up to conclusions, but it's quite possibly not as accurate because of these things, such as the population standard deviation is unknown. The sample size is small. It's unknown if the sample comes from a normalized distribution. Okay, the next point. So there's a lot of things I said there, but if you take a look at this, the red line, that is the T distribution curve. That's what that represents. So T distributions have fatter tails. And then as the sample size increases, it becomes closer to the Z distribution. And that's because as our samples get larger, we actually have better data to work off. And it's a way that the distribution works, that it gets closer. And then the more let's see. Oh, the T distribution is more realistic since true population means are rare. So I've mentioned it a couple times in this course, especially when we first started doing continuous distribution calculations. The continuous distribution calculation is not as realistic of an example, and it's because we don't have population data all the time. So once we start looking at the sampling distribution and then we start looking at the T distribution is really practical because anybody can kind of go out and do this, where you don't always have the population standard deviation. If you think about it in your life, as you'll see in this, you can go and you can do the T distribution studies a little bit easier than you can the population distribution, the Z distribution type of studies, because we don't have population standard deviations usually. Let's see, this other one down here is used to compare extremes in sample means. Okay, so we can use this to compare extremes in sample means. Okay, will be used in a large number of calculations, including confidence intervals and hypothesis testing. So as I mentioned, we're going to talk about confidence intervals, and this actually will be the first part of this video will be theory, and then it will go into the application. The application of these types of calculations with confidence intervals, they're not complicated. They're I would say at all, but they're pretty much not complicated at all compared to some of the things we do. So we don't do hypothesis testing in this video, but we will next week when I make that video. Okay, so the big deal here today is we're going to learn a new table. It's the T distribution, which has a table, and the table is quite a bit different than the Z distribution. So let's see, the T distribution consists of a distribution of curves. So there are many T distribution curves, and that's the big part of why we have a table like this. And it says the individual curves relate to the degrees of freedom. So, and the degrees of freedom are usually represented as n minus 1. Now, I'll discuss it next, but the reason why we have the minus 1 is because we have an inaccuracy inherent in this calculation that we're going to do. And because we are estimating the population standard deviation, we have to go and account for that. And theoretically, the best way to account for that is decreasing the n value by 1. And so it's an adjustment because of an inaccuracy built into it. Okay. Discuss next in the significance. Okay, it says for t-distribution confidence level calculations, use the two-tailed t-test and select the significance level from the table that added to the confidence level equals 1. Okay. So this is how, this is how this works. The confidence level is the beta plus the two-tailed test of significance, which is alpha, equals 1. Okay. So example, calculating the 98% confidence interval for the t-distribution requires one to find the t-score. If the sample size is 8, meaning n equals 8, and a 2% significance level for the two-tailed distribution will be used, as well as the appropriate degrees of freedom to locate the related t-score from the table. Okay, so for this, we have to know the sample size. So before we can use this t-table, we have to look at the sample size, and we have to know the significance level. Now, before we were looking at we've looked at the essentially we've looked at the percentages and the way that well, we haven't gotten into it too much yet. So for these 2% significance level is essentially, and this is what it talks about up here, the inverse of it is we're looking for the 98% area on the inside of the curve. So when we say 2% significance level, what we're actually doing is we're looking at 2% out on the edges and 98% in between the edges or the tail. And that's how that works if it was a two-tailed distribution. Let's see. And then we have to look it up with the degrees of freedom. Okay, so we have the degrees of freedom, and our n in this case is 8. So we're going to have 8 subtract 1. So we have right here 8 subtract 1 equals 7. So our degrees of freedom are going to be 7. And then this is a little way that we write out what the inputs are that goes into the numbers that make up the t-score. And so we write them down here like subscript. So it's like t, 2%, and then 7. So that's the 2% significance level, and the 7 for the degrees of freedom. And so when we look at about on the table, we have to have both of these. So what we do is we come down here, and this is a little snapshot of what the table, at least the table that I use in my classes, looks like. Is we go down to the degrees of freedom and make sure you remember it's the degrees of freedom, not just the n value. So it's 7. And then you go over, and if we're looking for the two-tail test, you have to find the right one right here. It says two-tail test, 2%. And then we go and we take a look at where these intersect, and it says 2.998. This is our t-score from the table. Let's see, it is not a probability. It is just like the z-score for the normal distribution. So the big deal here is that we use this table to find t-scores, which are just like z-scores. So if we think about this, where with the z-distribution, we go and we look up with a z-score, and we get this area under the curve value. So the actual t-table does not give us an area under the curve value. The t-distribution table, putting in those inputs, gets us to the t-score. So it's different than the z-distribution table. The z-distribution table actually is very dynamic, and there's about 3 different ways to use it, and I haven't shown them all yet, but the big deal here is the t-table. We put in the degrees of freedom and then our significance level based on whether we're doing a two-tail or one-tail test, and we get the t-score, okay? And we'll pull up the full t-table in a little bit. Let's see, so this talks about the degrees of freedom, and the main thing which I spoke about is when we have an inaccuracy, there's a couple different ways to look at this thing. Fundamentally, the issue is because we are estimating our population parameter, because we don't have a population, the population parameter, meaning the population standard deviation. Because we don't have a population standard deviation, we're estimating it, and because we're estimating it, we are introducing some inaccuracy and lack of precision into our calculation. So we have to decrease our n by 1, and that is essentially one of the ways of explaining why we subtract, why we have n minus 1. And if you look at the standard deviation calculations, you'll see the n minus 1. So it's the same exact thing, and it's the same reason, because with the sample standard deviation, when we do the sample standard deviations, we are introducing a little bit of a lack of precision in the calculation. Confidence intervals. Okay. So in inferential statistics, we have two primary methods of coming to a conclusion, type of thing, or making decisions. One of them is hypothesis testing, and it produces a point estimate. So with a hypothesis test, we say, if we were to do something, what is the likelihood that something will be greater than or less than or equal to something, and that's the single point part. And with confidence intervals, it says confidence intervals resulting in resulting in a range of values above and below the population parameter. So with the confidence interval, what we're saying is we are coming to a conclusion, or we're trying to figure out what the probability is based on, we say, what is this interval? What would be the interval to a certain degree of certainty that the actual population mean lies within, accuracy of say 5% type of thing. And so we have, and then we get these numbers. And so it's based on trying to come up with a range of where that actual mean is. That's what confidence intervals are. People confuse that, but it's our confidence level of a range of where the actual mean is, and that's what it is. Now, we're either wrong or we're right. So either the confidence interval falls within that range or it doesn't, but it's not both. So that's something to think about. This is a lot of the ways this is laid out. You'll see that a lot of this we've already seen. So let's see, student t-distribution confidence interval related. So this is sample mean formulas. I say sample mean because we have proportions too. Okay, confidence interval for mu with the standard deviation, population standard deviation unknown. So we use the t-distribution. So you'll start to see this where I say, we're looking for mu, but we have an unknown population standard deviation, or you'll see the size of the sample, and then it will say whether the sigma is known or unknown. And so in this case, unknown population standard deviation, and we're looking for mu, so we're going to use the t-distribution, and this is the formula for this, for the confidence interval. And so this shouldn't look too bad. We've already done this right here. We've changed up maybe the values just slightly, because before we actually had the standard deviation up here, there was the population one. In this case, I'm gonna zoom in just a little bit. In this case, we have a sample standard deviation up here. So it's the x bar plus and minus. When you see plus and minus, it means we produce the calculation for it being plus, and then we run it for it being minus. And then this is our t-score that we're going to get from the table, and it's the t-score multiplied by the sample standard deviation over the root of n. And that's all it is. These calculations, like I said, are not bad. The standard error, which is when the population standard deviation is unknown. This is the standard error part, and this is what this does. And the standard error is essentially saying that it is an estimation of the population standard deviation. And then the margin of error for mu with an unknown standard deviation, population standard deviation, this is the actual margin of error value right there. To actually write out the margin, then you would actually do the plus or minus whatever the x bar is. But this is actually the margin of error. So you would take this value and you would add it or subtract it to get that margin, to actually get the interval range. Let's see, for the z distribution, very similar. It says confidence interval for mu with standard deviation known. So in this case, we do the same type of setup, except we have a z-score. And then we have the standard deviation over the root of n. And then very similar, except right here, it is the population standard deviation over the root of n. And then same thing down here, margin of error for mu with population standard deviation known. So same type of scenario. So we see that z, that's just the z-score. Okay. And then for proportions, same type of scenario. We've already done these. So some of these have the little squiggly lines. I think in some of my notes I had the p bar. Same, it's the same type of deal. It's if it's a different hat, don't worry about that with this. So it's the same type of deal. We have the proportion, and then in this case, plus or minus, and then the z times this. And then standard error, it's this whole part. And then margin of error is the z times this part. And we'll look at how this works. Okay, this is the background theory of the confidence intervals, and it talks about, you know, that we do confidence intervals to provide an answer of how to deal with uncertainty. And it says in results derived from data that are randomly selected, a subset of population due to the possibility of misconstruing where the actual population parameter lies. The proper method of describing the interval is widely debated. So people don't say, you don't supposed to say the confidence interval, there is a 95, technically you don't supposed to say there's 95%, there's the 95% of the time it's between a certain range. What you say is within a 95% level of certainty, it's within this data. What that means is 5% of the time you have a 5% chance it's just not in there. And that's the way it works. And this is a little diagram that shows, it says, if you look at these different ranges of where a value is, some of these confidence intervals are not going to be where mu actually is, and that's what this is representing. So it says after all, if one calculates the 95% interval, approximately 5% of our time, the 95% interval will be wrong. So 100%. So 5% of the time, our 95% confidence interval will just be wrong. And that's because that's the way this works. It talks about also, like sampling distributions, the larger the sample, the closer one will be to the actual population value. In regards to confidence intervals, the larger the sample, the narrower the confidence interval will be. So the larger our sample of data, the more accurate we can be to how how wide that interval is or how narrow that interval is. When we don't have much data, that interval has to be really wide because we are not as sure as we would be if we had a lot of data. And it makes sense. We'll look at that too. Let's see. I think I mentioned a little bit of this. If one is to calculate the plus or minus z value for the calculation, one must find the correct z-score by dividing the confidence interval level desired by 2. The result will be half the probability of the confidence interval for a normal distribution when the probability values from 0 to 0.1 is okay. We'll look at this. Yin and yang, and this is the way this works. As we increase our confidence interval, the actual interval, the likelihood that we are wrong. So as we increase the beta value part, which is our confidence intervals, as they get larger, what happens is as they get larger, our actual confidence level will decrease in that it'll be more precise. Now, the issue is if we said, oh, we want a confidence interval down to 99% confidence interval that we're going to be right between a certain ratio, it's going to be really wide. And when I said the 99%, so the beta part will be the 99%, and then the alpha part will be the essentially 0.5 on each side, but that actual level will be really wide, and that's how this works. Mathematically, the relationship for the confidence interval is 1 minus alpha. For example, a significance level of 10%, alpha equals 0.1, is the opposite of 1 subtract 0.1, which equals 90, confidence interval. While this relationship exists between confidence intervals and significance levels, they are used differently. What is important is that one understands how they are related. Okay, to make it even easier, an annotated z-table is included with these notes too, so many of the common values are available. Let's see, the annotations link the value to the z-table probability under the curve to the context of which they are frequently used in examples listed below. I'm going to zoom in, but I will show you how this works. So what it is if somebody said, okay, I want a confidence interval, and this is all z-score confidence interval, because with the t-distribution it's much easier, but when we say we want a 90% confidence interval, then you would go and you would say, oh, well, if we just take a look at this blue one right here, it says confidence interval 90%, and then we get a z-score of 1.65, and that's the confidence interval for that. And it shows what the actual values under the curve go into making that 1.65 and what it would be. And then we have the one-tail hypotest. We're not going to have to use this for this video, and the two-tail hypotest. Okay, and the hypothesis is what that means. So there's one of these for each one, and I'll show you how this works. Of course, there are only certain ones that I chose to make this for, because these are the more common ones that come up. Like I said, this is only the z distribution part. Like I said, the t-table is much easier. Okay, so this is the z-table. Let's see, it says find the z-score for 95% confidence interval calculation. While this example shows the procedure for obtaining the z-score, it is similar to other confidence interval calculations. Let's see, 95% divided by 2. So confidence intervals always have two sides. So with hypothesis testing, they don't. But with confidence interval, it's an interval. It's plus and minus, so we have two sides, with the mean being in the middle. So we have 95 divided by 2 equals 0.475. So this is how we would do this normally just with a table. like I said, most of the time this is going to be easier because you're going to use that little annotated box I gave you. So this says, okay, 95 divided by 2 equals 0.475. Now we look up, using the z table, the probability value from 0 to 0.5 on the table, and we're actually looking for this one right here, 0.475. So it says locate the value to the left of the margin, 1.9, and the value on the top of the table, 0.06. Okay, so let's say we're looking for this right here. We would have to find the closest value to that, and it is 1.96. So if we look this up and we're looking all around this table first, we would look for this value, which is that half, and then we would go out and we'd locate 1.96. And we would add these two together and we get a z-score of 1.96. So you see, I took the way that we use the z-score. I didn't invent this, but I took the way that we use the z-score, and instead of going from the left column out here and then going across and finding it from the outside, we looked at the inside and then we figured out what the z-score is from that. And that's how we have to do this with the confidence intervals for the z-scores. So for our calculation, we would use 1.96. Now, I'm going to go back because I was talking about how to use those annotated sections. So in this one, it says, find the z-score for 95% confidence interval. Well, let's see what it looks like. 95%, right here, 95% confidence interval, 1.96. And it says 0.475 plus 0.475. There you go. I already laid it out for you, right? That's why it says, just when you thought this was getting complicated, Mr. Ferb makes it easy. There we go. So, of course, there's only the common ones that are laid out. And now I'm going to back this up. But this is how you look it up if you... if it's not one that's already there. Most of my stuff, it's already there. But this is how you would do it on most z tables. You don't have the annotated sections down below. Okay, and now we're going to go on to the step 2. So we found the z-score for the 95% confidence level. And it says confidence interval. So it says when calculating error or error-bound mean, one uses the same calculations as the sampling distributions. And so this talks about it. If this was a t-score one, we would be using this. If it was the z-score one, we're using this. If it is a proportion one, we use this. So it says, for example, for a population standard deviation of 2.4 and a sample size of 32, the error-based mean would be this. Okay. So that's not bad. Putting it all together, it says to make the example complete, we'll complete the confidence interval with a sample mean of, let's say, 14. So if we had 14, and then we had the z-score of 1.96, and then our error-based mean, the mean error part, it is 0.4242. Then we'd put it all together, and we would calculate this with the plus, calculate it with the minus, and we would get 13.1685 and then 14.8314. Now, some people leave it like this, and that's not, I think sometimes in my homework I have that there's not a problem with that. It's just saying this is what the answer is, calculate it with the plus, and then you get the plus side, calculate it with the subtraction, and you get the low side. So sometimes textbooks will leave it like that. Sometimes they'll actually just calculate out the actual bounds. So that's okay. Okay, now we're just looking at the examples of what we talked about within this whole context of the theory part. Now we're applying it. So it says calculate the 95% confidence interval estimate for the population proportion of interest based on, so this is a sample proportion of 35% with an N of 80. In addition to the confidence interval, what is the standard error? So this is the formula that we'll be using. And so when we're looking at 95%, we can look that up, but the z-score is 1.96. That makes it easy for us. Like I said, we can look that up. I'll pull up the z-table. So on the z-table, this is the way it looks. The z-table I give you. It looks messy, but there's a reason why it's laid out like this. So what you would do is you would go, this is a really common one, so you'd probably remember it after a while. You would go, where is that one? Where's that 95%? So there's 98%, 90%. This one's 95%. And then we have 99%, 80%, 96%. So it says 95% confidence interval, 1.96, and then it shows 0.475 plus 475. Now, if we follow this up, it has 0.4750, and then if we go out, it says 1.9, 0.06. So this shows you how this goes together. Okay, so that's how the table is laid out, like that. Okay, I'm gonna back this. Okay, so let's see, we have the z-score. Then we would just do the math right here, which we did with the sampling distribution, same type of math, the proportion sampling distribution. We would get the answer there. And then you just calculate this for the negative and calculate it for the positive, and we have our answers. And this is our standard error over here. Okay, that's our standard error. And then let's see, how do we do this in the calculator? So we do if we do this in the calculator, we do the TI-8384 calculator, we do one prop z int, and I believe this is, I don't have a calculator in front of me. It's either in the dist or the stats key. I'd have to take a look. That most of our calculations are in the second dist or the stats key button, and in there. I'm not positive which one it is. Some of them are easy to remember where they're at. Let's see, the x is the number of success in the sample. Now, so 0.35, and so the number of success in the sample would be, in this case, 0.35, because it's 0.35, and then 80 times 80. But here's the deal. So that whatever value that would be, you can actually put it in just like that, and as you move to the next line, it'll calculate it. Now, if it comes up where it's not a integer, you have to round it to the nearest integer. You'll get an error if you leave it with a decimal in this part, because the success cannot be a fractional success. It doesn't work that way. Let's see. It says the easiest way to obtain this value is to multiply. The easiest way to do it is just to, which is what this is, n times the sample proportion hat. And like I said right here, you just do it right there. And then you put that in. Like I said, if you get an error, this has to be an integer. And then you put in the 95% level, and you are good. You have the answer. Okay. So let's take a look at another one. Calculate the 90% confidence interval estimate for the population proportion of interest based on p-hat of 0.45 and n of 60. In addition to the confidence interval, what is the margin of error? So in the other one, this was the standard error, and it's also known as the error-based mean, this part right here. Okay. So standard error is also known as the error-based mean, which just kind of saying that this is the standard error that we get. Now, it is not the margin of error, because the margin of error is actually the standard error or error-based mean multiplied by the t-score or the z-score, because that's actually the margin, that's the range. And if you think about it, when we hear the word margin, we're thinking of a range because the standard deviation is involved. Okay, so for this one, same type of scenario, you would look up your 90% confidence interval of 90%. So you'd look up 90%. So we go and we find 90%. Like I said, if we're going to do this backwards, we would take, like, without having this stuff annotated, you would do 90 divided by 2, and you get 0.45. So I see this is right in front of me, but we would go up and we'd find the closest one, and it would be, well, right between this and this. And what I have found is most people use this one, the 1.65, and not this one. Go figure. I don't know why. Technically, it'd probably be more accurate being 1.645. But this is what most people go by. So it is 1.65. So we have 1.65 right there. We do the math on this one. Okay, so this is our kind of our range within that range proportion figure, we can say. So we do this math right here, and we get this. And then we just go and we multiply it by our z-score figure, and we get the margin of error. So the margin of error is all of this together. And then we have the negative side, the low side, and the high side. We do the math and we get that. So then on this one, we do the same thing. So just put in the 0.45. And then the 60. Like I said, if this comes out to a decimal, you need to make it an integer, so round up to an integer. I believe you usually round up, but if it's, you may want to try it two different ways. And then 60 and the confidence level. They say confidence level, but it actually means confidence interval of 90. And then you get your answers. Okay, so this one is this is a non-proportion type of one. And this one says calculate the 96% confidence interval estimate based on, so sample mean of 78, population standard deviation of 20, and n is 40. Same scenario. This is the goal, getting all the pieces for that. So the 96%, the 96% confidence interval, the z-score for the 96% is 2.05, and so we would look at this and we'd say, which one is the 96%? And we'd find that it's over here on the orange. This is 96% confidence interval, 2.05, and it actually is made up with these values right here. These are the closest. So he said so it's 2.05. Okay, that's how that works. Okay, so 2.05, and then we do the math right here, and we get that value. We multiply these together, and that's our margin of error. So that's the error part multiplied by the standard score part. In this case, it's the z-score. Now, when we do this in the calculator, it says use the given standard deviation stated in the problem, not the calculated. So in your calculator, there are times where we use the normal CDF function, and the normal CDF function is based on working with populations. So in the sampling distributions, I always tell students, if you're doing sampling distributions and using the normal CDF part of the calculator, you have to put in the sampling distribution of the standard deviation of the sampling distribution, okay, for those problems. So you're putting the calculated standard deviation in for the z intervals or the t interval. You have to put in the given, and that's because your calculator, because this is the interval, your calculator knows that it is essentially not the, it knows how to do the math for you. So it's inherent in there. They know that they are working with what would be more of imperfect data, so they actually do the math. And what happens is you put in the standard deviation part, and you put in the 40, and it will calculate this for you. So it actually does that for you in the calculator. Whereas, like I was saying with the sampling distributions, you have to put in this, the result of this value in as that one. So this one, just put in what they give you. And so that is a change from my prior lesson where I told people to put in the calculated one. This one you don't. You put in the stated one. So you have to play with these things. So you put in our values, and there we go. And if we are a little bit off, it's not a big problem. Remember, we're using the tables, and the tables, sometimes we have to pick which one to use type of deal, and the calculator is usually more accurate. Z interval. Okay, so this is another Z interval one. So I will probably skip this one for time for the video. I want to, so this is just like the one before. This one's a 90%. Okay. And the standard error. So this is, says, and what's the standard error? The standard error is this part. Remember, standard error is just that. The margin of error is that part. Right? The margin of error is that part. Actual confidence interval, the whole thing. The high and the low, both of these. So confidence interval, the whole thing. Low number, high number. Margin of error, just the part that goes above and below the mean, just that segment. And then the standard error, just that part. Okay. Okay, well, let's look at the t-distribution. We need to look at this, so focus on this a little bit. Calculate the 99% confidence interval estimate based on a sample mean of 3.13, the sample standard deviation of 1.2, and n of 20. This is what I usually do. Usually with t-distribution problems, I will give you an n that's less than 30, and that will kind of key you in. Oh, this is, and I'll give you an S, not a sigma. So this is a sampling standard deviation. Okay, so this math should look really similar from what we've been doing. Remember, degrees of freedom. We use degrees of freedom with the t-distribution. So it's 20 subtract 1 equals 19. And then this is the little thing where we write out, you don't have to do it like this, but for your own sake, you probably should. You write out the inputs that get you the t-score. And you do that so that when you go back and if you make a mistake, you can see what inputs you put in. Otherwise, it's just, where did you get that t-score? You don't know. So 99% and then 19. And we're going to look these things up. Now, remember, this is 99% and 19. Just remember that. The way that the table is laid out is it's a little different. So that was 99%, 99%, and 19. Okay. And it's two-tail because it's confidence interval. We have both sides. That'll come up different lesson. Okay, 19. This one's easy. We go to the 19 first. I'm going to zoom in. So we go to this range. So this one's super easy to find. I'm going to try to highlight these going across. Okay. Now the question is which column do we pick? And we go to two-tail. Now, the questions, confidence intervals are usually written in the large space, the beta space, the big parts underneath the curve. But the way that the t table is laid out, it's laid out by making you select the alpha portion, which is the little tail part. So if we're looking for 99, we're going to look for a two-tail 1%. Two-tail 1%, and that's because we have 99%, which is our beta. In this case, our alpha is 1%. Two-tail is actually split, but 1%. And so we're going to use the 1% significance level on this table. And our answer for our t score is going to be 2.861. 2.861. Okay, like I said, this gets us the t-score. This does not get us the areas under the curve like the z table does. Okay, that's a big difference, is that we do all of this just to get the t-score, where with the z distribution, the t-score is easy to get, right? We can go further with the z table. So it was 2.86. Okay. It has 2.861. That's fine. 2.86. So, boy, that almost looks like it's similar. Okay, so this is our t-score, and then we go and we get the other component, which is this part right here, and we put these together, and then we'd multiply these, and then we do the subtraction, do the addition. We have the low side, we have the high side. Okay, now if we do this on the t interval, like I said, it's either in second dist. I don't have one of the calculators in front of me. Second dist, or it's in the stats key of the calculator. Let's see, and then what we do is, let's see, the SX, that represents the sample standard deviation, so that's what that means. And this points out again to use the given standard deviation stated in the problem, not the calculated. And it's because in this case with the t intervals, they know that they're estimates, and so they know kind of what you're doing with it. You're not putting in really good population data in this. They know that what you're putting in, and so it kind of does some of the math in here. So it's a higher level program than the other ones are, or the other ones are a little bit more versatile, I guess. And then for the C interval, you put in 0.99, and it gives you the answer. It should be pretty close, not perfect, but close. And that's because the calculator is just more accurate. Okay, let's do one more of these. And then I have more videos on this. So if you're watching this video, I have other videos where you can practice this, and I'll go over I pull up the calculator too. Calculate the 90, I use the 99% again. That's too bad. I should have picked a different one. Oh, but the n is different, so our degrees of freedom is different. We'll get a different score. Okay, calculate the 99% confidence interval based on, so x bar of 5, sample standard deviation of 3, and n of 10. Okay, and here's our calculation. Our degrees of freedom are 9, and we're doing the 99% again. But because our degrees of freedom are different, we should come up with this one, 3.24. So 9 and 99. 9. Nine and 99. So we do the two-tail right here, and 9. So it is the 3.25. Oh, so this one says 3.2498. So it's possible I did get this from a different example, or I'm suspecting it's more accurate. So don't get too concerned if you're like, hey, this isn't the same. This is very, very similar. I get examples from different sources sometimes. And then what we just do is we calculate the other component to it, the 3 over, man, 3 seems, these numbers are pretty small. So 3 over the root of 10. So we do that. And then we have the plus side and the low side, the subtraction. The high side is the plus side. And we have our answer. Okay, I just want to go back and reinforce one thing real quick. And that is, I just want to go back. So there are a couple terms here that I just want to reinforce. And that is the error-based mean is this rightmost part. Okay, so it's not the z-score. It's not the score part. It's the part that deals with the sample standard deviation over the or the population standard deviation over the root of the n. So that's the error-based mean, and it's also known as the standard error. Okay, so the error-based mean, standard error, same thing. And then when we put them all together, we have the margin of error, because this is kind of the range of that margin. Now, this isn't actually the actual confidence interval. The confidence interval is the whole thing. It's the low and the high. Okay, maybe at a later date I'll point that out a little bit more clearly. Okay, thank you.